Feel free to ask me any questions if you have any. I'm just setting up some stuff for class. Get more people coming in. Feel free again to ask me questions. We got about 1 minute left. I'm trying to write up some stuff. I got another person. All right. Okay, so as asked, or as I had asked, if anybody has any questions, now's a good time to ask them. You can type them in the chat, or you can just blurt them out. It's all good with me. It looks like we don't have any. I'll give a couple seconds to make sure, but we are going to start into knocking out the remaining part of chapter 9, and that's going to entail me doing some calculations of center of mass. I know your class was lucky enough to actually for me to actually cover a single center of mass calculation. So you have that advantage, but I'm going to, since you have that advantage, I'm going to give you another one that's a little bit more complicated to do, as well as a couple discrete ones. So I think these will be some good practice for your class, as well as any other students that might check it out. So hopefully you'll enjoy that. I'm going to, as I said, doesn't look like we have any questions. I'm going to go ahead and share my screen so that you can follow me on this first problem, where I basically have a what in your math class would be called a homogeneous lamina. And a homogeneous lamina basically means this is a lamina, so it's like a very, very thin two-dimensional shape. In this case, it's shaped like a triangle. And the homogeneous lamina, since it's homogeneous, means that it has about the exact same mass over every square centimeter as it does over every other square centimeter. So that's what I mean by that. So if you imagine that triangle that you see there as a quote unquote homogeneous lamina, what I mean by that is it is a 10.0 kilogram plate that's triangular in shape whose mass is uniformly distributed. Now, by some magic of physics or whatever, we've managed to secure three very small masses. And I said small masses because I want you to consider them as if they're point masses, even though their mass is quite large. Three small masses, M1, which you can see is centered at the origin, M2, which you can see is centered on the bottom right corner of the triangle, and M3, which is 50 kilograms, is centered on the bottom, or excuse me, the top right vertex. So we basically got these point masses at the vertices of the triangle, and the triangle, of course, has a mass as well. So when we go to calculate the center of mass, which is what the question is, when we go to calculate that, we're going to have to take into account the effect of the plate as well, the triangular plate. Oop, left off of that. So one thing I'm going to make use of is a rule that well, I sort of derived it for you already. I told you how it actually came out to be. But if you actually do like a right triangle or something like that, and you try to calculate the center of mass of it, what you can do is if you want to find the x center of mass, you want to move either to the left or to the right because that's parallel to the x-axis. But you start on the pointy part and move towards the fat part. So in this case, the way this triangle is set up, you're going to move from the origin to the right. And if you go like this, you can see it's getting wider and wider and wider. When you're doing that, the center of mass will be 2/3 of the way from the narrow part, which is at the origin, to the fat part, which is at the 3-meter mark. Okay. So our x center of mass is going to in fact be 2/3 of the 3 meters. So that'll be 2 meters. Now, when you're doing the y center of mass, you have to move either up or down because in this case, our y-axis is drawn in the up-down direction. And again, you want to start at the thin spot, which would be that top one. And then you go down and you can see it's widening and widening and widening. Again, the center of mass will be 2/3 of the way from the narrow part, which is the top, to the fat part, which is the bottom. So we're going to go down 2/3 of the 5 meters from the h equals 5 meters towards the h equals 0 meters. That is the same thing as 1/3 of the way up along the 5 meters. So that's going to be 5/3. So I'm making use of that definition or of that rule that we've learned regarding the center of mass of triangular plates. Okay. So let's start by reiterating exactly what formulas we're going to use. So here's the solution. What we're going to make a use of is the x center of mass is m1 x1 plus m2 x2 plus dot 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 plus m sub n, where n is the total number of objects, discrete objects that we had, times x sub n. All of that now has to be divided by m1 plus m2 plus dot 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 plus mn. Okay, that's your center of mass formula. And then the other part I'm going to make use of is this. Actually, that last part was not drawn very well. Okay, for a triangle, the center of mass is 2/3 of the way that way and 2/3 of the way that way. So that's basically what we're doing here. So it's roughly like that. Okay. So in this case, I'm actually asking for the center of mass, but this is two-dimensional, and it's not highly symmetric. So I actually have to calculate the center of mass for both the x coordinate and for the y coordinate. So let us begin. The x center of mass is going to be, first off, I'm going to point out the actual mass and X for the triangular plate. So the mass for the triangular plate is 10.0. I'm leaving the units off just because it's kind of a cumbersome to write all that stuff and it takes a long time. So just that's something you definitely want to pay attention to make sure everything works out. But in this case, I'm totally not writing it down, but I am paying attention to it. So the center of mass, at least along the x direction, is 2/3 of 3.00 meters. If you multiply 2/3 of 3.00 meters, you get 2.00 meters. So I'm just going to write this by saying this is 2/3 of 3.00 meters. Okay, so hopefully that will be enough to remind you when you look back at it. I know that was the number one question a lot of my students had when I did this in lecture, face-to-face lecture. So now I've taken care of that mass. I also have mass 1, which is 25 kilograms. And of course, that has a x coordinate of 0. Notice I'm just picking off the x coordinate. I don't care about the y right now. I also have a 30 kilogram mass, and that one has an x coordinate of 3 meters. And then I also have a 50 kilogram mass, and that one also has a x coordinate of 3. And then all of this has to be divided by the total mass, which I don't have to actually add them up on actually showing it on here. I could just add them up in my head and put the result down at the bottom. So 10 plus 25 is 35, plus 30 would be 65, plus 50 would be 105. Wait a second, 65 plus 55, that'd be 115, right? Okay. So this is going to be 115, and all of them had one decimal place. So I'm going to say 115 kilograms. 10 plus 25 is 35, plus 30 is 65. 65 plus 50, yeah, that's 115. Okay, so we got all that. Now I can go ahead and do the calculations. I'm going to say 10 times 2 plus 25 times 0 plus 30 times 3 plus 50 times 3. Now, before I do this, it really would be advantageous of me to physically guess roughly where it will be. I know the plate generally should have a center of mass at around the 2-meter mark, but I also know that the M2 and M3 are quite a bit bigger. Excuse me, quite a bit more massive than the plate or than the mass M1. So all of that's tending to move the center of mass even further to the right. So I'm going to estimate somewhere around 2.5 meters is the center of mass for the x direction. So let's give that a try. When I actually do the calculation in the numerator, I get 260. So here's 260. 2 times 10 was 20. That should have given me, of course, 3 sig figs times 3 sig figs. So that's just one decimal place. So that gives me one decimal place. 30 times 3 would give me 90. Again, 3 decimal places would be one decimal, or 3 sig figs would give me one decimal place. And 50 times 3 is 150. In that case, it'd be a single, or actually, no, in that case, since it's 3 sig figs times 3 sig figs, the 150, the 0 in the ones place would be the last sig fig. So this one technically is not a sig fig. And the units, this is what I meant by keeping track of the units. The units are going to be kilograms times meters. And then I'm going to divide all that by 115.0 kilograms. So I take the 260 and I divide it by 115, and that gives me 2.26. So I was a little over ambitious by assuming it was 2.5, but it's 2.261. So this is 2.261 meters. Obviously, I had 3 sig figs divided by 4 sig figs, so the result should be 3 sig figs. So that's one extra digit there. and this is equal to the X center of mass. I'll explain a little bit about what that means towards the end of the problem, but not right now. Any questions on that part? Okay, so this is the formula that we use for a discrete distribution of masses. And I've made it a little different than most of the examples you run into in books and stuff. This one included an actual physical body, the triangular plate, and then I pretended like the three masses were point particles. But you can do that. I mean, any mass you have, if you know where its center of mass is, you can pretend like it's a point particle, and that just works out fine. So that's what I did with M1, M2, and M3, is treat them as if they're point particles. Now I'm going to continue doing that this time for the YCM. So for the YCM, it's the same formula. So I'm going to say 10.0. That's the mass of the plate. Now in the YCM, this is going to be 1/3 of 5. 5 divided by 3 is, of course, 1, because 3 goes into 5 one time and it's 2 left over. So it's 1 2/3. So I'm going to write this as 1.667. Just carrying an extra sig fig there for the heck of it. And I'll put a reminder here in case someone's looking at it later that this comes from 1/3 of 5.00 meters. And remember, that's 1/3 away from the fat end. So it's 2/3 away from the thin end. All right, now that I've got that one, I can also include the 25, so 25.0, but that also has a y coordinate of 0. Those are technically called abscissas and ordinates. The abscissa is the first one and the ordinate is the second one. So the ordinate here is the 0. And we'll we'll file that under categories that only Mr. Younger remembers. So anyways, I'm really interested in the names of things. All right, the next one is the 30 kilograms. So I'm going to write 30.0. And now that one has a y coordinate of 0 as well. And then finally, I'm going to write the 50.0. And that one has a y coordinate of 5. So it's 5.00. And that's the entire thing. Now I got to divide it by the entire mass, which is 115.0. I'll just leave that kilogram part off because I didn't put any units here. Now, again, before I estimate this answer, I've got a lot of things pulling it towards being around the 1.667 as the center of mass for the y coordinate, because I've got a 25 kilogram mass and a 30 kilogram mass. And I got the 10 that lines up right there as well. And the 25 and the 30 would tend to make it even closer than 1.667 meters up from the x-axis. So I'm going to say in this case, is because I overestimated last time, I'm going to say this one's going to be roughly, instead of 1.6, let's say 1.5. That's what I'll say. Okay. So that's my estimate. And again, this is just physical reasoning, and it helps us learn better about these things by predicting it and then getting an answer and finding out whether or not it's right. So I've got 10 times 1.667 plus 25 times 0 plus 30 times 0 plus 50 times 5. So I've got 10 times 1.667, 25 times 0, 30 times 0, and 50 times 5. Adding all those up, I get 266.67. And that would be units of kilograms meters. And all that's going to be divided by 115.0 kilograms. We know the sig figs places are right in the denominator. The numerator, when I multiply 10 times 1.667, that's 3 sig figs times 3 sig figs. So that gives me 3 sig figs. And the number is going to be about 16.6. 7. So using 3 sig figs means I only get 1 decimal place. The 25.0 times 0 gives me nothing. The 30.0 times 0 gives me nothing. But the 50 times 5 gives me 250. And that's 3 sig figs times 3 sig figs. So that's really only to the ones place. So both of these decimal places are not sig figs in this one. So now if I take that 266.67 and I divide it by 115, I get, I was off this time too, 2.319. So this is going to be 2.319. Notice the kilograms meters divided by the kilogram is just a meter. And of course, that was 3 sig figs divided by 4 sig figs. So this 9 is an extra digit that's not a significant digit. And this is YCM. Okay. So that's our answer. And in fact, what we're looking at here is if this thing's supposed to be 5, then 2.319 is quite a bit less than midway. And midway is roughly here. So what I would say is maybe the YCM is along that line. And then the XCM, we found out that was 2.261, which is more than 2/3 of the way to the 3. This is 2/3 of the way. And I go a little bit further. So what I'm going to say basically is maybe this is roughly where the XCM is. And what that means is roughly right here is where you'd want to hold your finger up, and then you could balance this triangular plate on your finger at that particular point. Assuming, again, the XCM really is 2.26, assuming that that dotted line really is at 2.26 meters. And the Y one is at 2.32 meters. If I actually took the time to measure that out perfectly, then yeah, my finger would balance it perfectly there. So I could sit it on my finger and it would stay and it wouldn't do any of this. It would just sit perfectly still. So that's one of the definitions of the center of mass is the point under which you can suspend something or above which you can prop up something with just one point of support. Okay. But it also happens to be, for instance, if I took that configuration, those 3 balls that are attached to that triangle, and I tossed it like this, by tossing it, it would probably spin this way and fly off. Well, what would happen in such a situation is the center of mass would move in a nice parabolic trajectory, just like what we calculated in chapter 3 when we learned about projectile motion. So the center of mass is what would actually carry out that parabolic path. But if you took the time to actually make a mark, say where that center of mass is, and then make another mark somewhere on the plate, say, and the further away from the center of mass, the better in terms of just being able to accurately measure it. You could put another dot, and then you just connect the dot from the center of mass to the other dot via a line. And if you knew when you released it to throw it like a projectile, if you knew at what orientation or what angle relative to horizontal that line was when you released it, and you knew at what rate that plate was rotating, then you could predict the orientation of the whole thing at any point in time, and even at the point in time at which it's about to collide with the ground. So you could even predict exactly how far the center of mass is up above the ground when it hits. That's sort of what we're going for here. Is as you read chapter 9, you'll realize we're learning these techniques of finding center of mass for discrete objects as well as for continuous or continuous objects. But what we're ultimately pointing to is there exists a Newton's second law that your book takes the time to derive that says basically if you take the sum of all the forces acting on a system then the sum of all those forces acting on the system will give dp dt, the momentum of the system. And what that means is the center of mass will move like a point particle, acting as if all the mass is located there at that center of mass. And then you could have a secondary equations about rotations and stuff, and that would actually tell you the orientation of the object. But the actual object's still going to behave like a single point object. But if you want to know its orientation in space, then you have to have a second equation. So that's really what we're shooting for, is the ability to solve a problem for a complex shape or a collection of items, that kind of thing. Anybody have any questions on that? Anybody have any questions on how any of this was done? All right, I still don't have the chat up. Let me do that. I don't know why this is, there it is. Okay. Now I've pulled the chat up so I can at least see that in case anybody types anything for me. So now that we've done this one, that is a discrete collection of objects, and one of which was a sizable object. So now I'm going to do another one. I've already done the simple triangle for you guys in our last class, so I'm going to stay away from that. But I decided I was going to do something a little more complex for this one. So here's what I'm going to do. I'm going to draw my coordinate system like this. Okay. This is going to be my y-axis. This is going to be my x-axis. And originally I was going to make a highly symmetric one. And then I was like, well, no, that's just taking all the complications out of it. And you need to be able to solve complex problems. So what I'm going to do instead is I'm going to say I've got a triangle that goes from the origin to that spot right there. But over here, I have a triangle as well that goes from this spot to this spot, from the origin to there. Okay. So it's an ugly triangle, and it's an ugly triangle that's not symmetric, right? So in principle, I could do this as two discrete objects. I could take the top right triangle that's cut from the bottom right triangle by the x-axis, and I could find the center of mass of that using my 2/3 rule. And then I could do the same thing for the bottom right triangle using my 2/3 rule. And of course, I have to discern what weight each one of them is, but that's not too hard, because I think you realize that the area of a particular plate is directly proportional to the mass of that plate. So in this case, I'm going to do it basically both ways. So what I'm going to say is this particular triangle has a mass of, let's say, 30.0 kilograms. Okay. I'm going to say that this coordinate right here is let's say 3.00 meters, and we might even say that's equal to h. Okay. This one's going to be w is equal to 5.00 meters, and then this one down here is going to be let's say d, and it's negative 2.00 meters. Okay. Assuming the mass is uniformly distributed, what, I guess I shouldn't have made a capital W there. What is the center of mass? So it's the same problem we did before, but this time we're actually going to have to use the actual continuum of matter. So we're actually pretending that atoms, or excuse me, that matter is not made up of little individual discrete atoms, but rather is sort of smeared out all over all space. So unless you're worried about dimensions that are comparable to 10 to the 10 negative 10th meters, then you're probably going to be fine by making this assumption. Okay. So here's our solution. And like I often do, the solution not only entails the solution, but it often gives you the equations that you're going to be using. And the x center of mass equation, for instance, is going to be the integral of x dm divided by the integral of dm. And I want to remind everybody that dm can equal lambda times dl, where that lambda is called a linear density, or a mass per unit length, and dl is a differential length element. So that's for like something like a bicycle spoke. Okay, if you wanted to try to find the center of mass of a bicycle spoke, it might be reasonable for you to use lambda times dl to specify the actual dm. If you're using a two-dimensional object, then it might be more reasonable to use a mass per unit area, which was the sigma here, times dA, where A is a differential area element. That's the one we're going to use here. Or finally, if you're dealing with a three-dimensional object, you're going to use rho times dV, where V is a volume. Okay? So that's what we're going for here. In this case, we can actually figure out what sigma is, and that's a little bit instructive. What I've noticed from years of teaching this is my students, out of let's say 24 students, probably about 20 of them just don't get what the heck sigma, lambda, or rho is. So I try to beat that in as best I can. And one of the ways I try to do that is, in this case, I would take that 30 kilograms and I would divide it by the surface area of that triangle, and that would be sigma. That being said, I really don't have to, because it turns out that the way you do this integral divided by an integral, both of them are going to have the sigma in it, which is a constant. That's what uniformly distributed mass means, is the sigma or the lambda or the rho is a constant. And because of that, the sigma is going to cancel out in the top and bottom. So you wouldn't even have to know it. But I do find it kind of useful. It would be 30.0 kilograms divided by 1/2 base times height. You might not be able to notice it here, but 1/2 base, we might say the base is that distance that goes from -2 all the way to 3. So that would be 5.00 meters. And we could say the height then is that distance that goes from the origin to the 5 meter mark. So that one's actually 5 as well. So we'd get 15 divided by 25, which you could reduce as a fraction to be 0.6 kilograms per meter squared. So that's what sigma is. I just, again, we're not going to need that, but it's worthwhile for you to understand what the sigma is. So that's why I took the time to do it. And I wrote it in purple so you'd realize that we didn't really need it. Okay, so let's start off by doing the integral of x dm. By the way, I have to find the y center of mass too, and that's the same formula except I replaced the x with a y. So that's why I didn't really write another formula, because it's so trivial to translate it to a y. All right, so the integral of x dm, when you go to take such an integral, you need that integrand to have a definitive x value that doesn't vary by much. In other words, the nearest part of x, closest to the origin, say, of the dm element, that shouldn't differ from the farthest point by more than an infinitesimal amount, or an infinitesimal change in x. By doing that, you avoid having to calculate some equivalent average x or something like that. So you want to keep that in mind. With that in mind, it's kind of weird, but what the way you can implement that is you can imagine a rectangle like so, and the width of this rectangle is dx, and the height of the rectangle is y2 minus y1. So I'm going to find out an equation for that edge of that triangle. And then I'm going to find out another equation for the bottom edge of the triangle. And the equation for the top edge of the triangle is going to be y2 equals mx plus b. And the y1 will be y1 equals mx plus b again. So I think you guys can see, I will write this over here. I think you can see that y2 should in fact be h over w times x. Notice the intercept is actually the origin, so y equals mx plus b means it should just be rise over run, which is h over w, times x plus b, which is 0. So that's what that is. Now, the y1, on the other hand, that has a rise of negative d and a run of w. So this one's going to be negative d over w x. But it also has an intercept of 0. So that's the whole thing. All right. So my dm, I can now say, is going to be of the variety sigma times dA, which is going to be the integral of x times sigma. Now, dA is going to be basically y2 minus y1 times dx. So I think y'all can all see that this is in fact dA, the rectangular area. Anybody have any questions on that yet? Okay, I'm going to pull this sigma out in front and just put it here, because remember, sigma is a constant because it was uniformly distributed. Okay. Distributed. Yeah, I think I shrunk my u. So I sort of have a distributed with a bi instead of a b. No, I did do bu. Okay, that's cool. So in fact, I know that the integral is going to go in the x direction. So I'm actually going to integrate from x equals 0 to x equals w. Now, can choose to just start using numbers. I'm trying to put the W's right now and stuff like that, so it's easy for you guys to see exactly what number I'm using. But in principle, I can go ahead and put the numbers in at any time. I'm going to go ahead and distribute this x to the y2 minus y1. So I'm going to have the x times, first off, I've got to write y2, which is h over w times x, and then minus. Now I've got to have the y1, which is negative d over w times x, and then all of that times dx. So you can see I actually get a minus, which gives me a plus, and now my integral becomes sigma times the integral from 0 to w again of, now I'm going to distribute that x. I'm going to have h over w x squared plus d over w x squared dx. That's pretty good because I can now write sigma times h over w plus d over w, because if you notice, there's a common factor of x squared I can factor out of that, and I would have h over w plus d over w times x squared. So I'm getting that times the integral x squared dx from 0 to w. This gives me, in fact, sigma h over w plus d over w times 1/2 x squared, which is just going to be w squared over 2. So notice I went ahead and did the integral, but went ahead and evaluated at the range. The integral was 1/2 x squared, and when I evaluated at x equals w, I got 1/2 w squared. And when I evaluated at 0, I got 0. So that's the whole thing. And I can leave it in that form. I could put the numbers in if I wanted to, but I can leave it in that form as well. So that's what I'm going to do. Now I got to do the other integral, which is the integral of dm. Does anybody have any questions about what I've done so far? No questions? Okay. I don't think I have, yeah. I don't think I have anybody in any waiting rooms. It's saying something weird about waiting rooms over here. All right. So the only difference for this integral and the one we just did is that x that I had in the integral. So I don't have that now. So in fact, what's going to happen is this is just going to be sigma h over w plus d over w, but instead of integral of x squared, I'm just going to have the integral x dx from 0 to w, which means this integral is even easier because the integral, oopsie. Everybody noticed that I made a mistake on my integral? Yeah, you can go ahead and type in your first and last name in the meeting chat too, just so you have it for your roll. I made a boo-boo. I integrated x squared and got x squared. I can fix that real quick. Everybody pay attention to this quickly. All I'm going to do is change this exponent from 2 to 3. And all I'm going to do is change this 2 down here to 3. Sorry about that. I don't know what I was thinking, but clearly I'd made a boo-boo and called the integral of x squared dx 1/2 x squared. That's just not right. All right. Sorry about that, everyone. Now the integral of x dx, that is 1/2 x dx. So now I can say sigma times h over w plus d over w, which obviously they have like denominators, so I could actually add them now. All that is going to be divided by 2 and then times w squared. Okay. So now I can say the x center of mass is actually equal to the first integral, which I'm going to write a little differently now. I'm going to say sigma h plus d over w times w cubed. So in other words, I went ahead and combined those two fractions since they already had a like denominator. And I'm putting the 3 down in the bottom because that's what it was. Okay. Now the other one is also a sigma, and it's also h plus d over w, but this time it's a 2w in the bottom and it's a w squared. So what I want to see first, and I should have done this up above, but basically you can see that this 3 is going to cancel out with this w down here and make it a 2, and this 2 is going to cancel out with this w down here and make this one a 1, like that, and this sigma is going to cancel out with this sigma. And now I can go ahead and say this is 1/3 parentheses h plus d times w squared over 1/2 parentheses h plus d times w. Now you can see that this w squared is canceling out with this guy. This h plus d is canceling out with this guy. And now we have 2 over 3 times w. So lo and behold, even though this is a weird triangle, it still turned out to be 2/3 of the distance from the pointy narrow part, which is at the origin, to the wide part, which is at x equals w. Any questions on that? So that's our x center of mass. And I'm going to go ahead and box that off so we can find it. Now we're going to do the y center of mass. So the y center of mass is a little bit more of a pain because now I have to uh, do the, well, for starters, I'm going to have to do the integral in two pieces, a piece for the top half and then a piece for the bottom. And I say half, it's not half, but a piece for the top triangle and a piece for the bottom triangle. Uh, Let me draw that again in a coordinate system so that we can make some sense of it. I'm going to draw a coordinate system in red this time. Oops, evidently I'm not. Okay, I'm going to draw a coordinate system in red this time. Okay, this is going to be my x-axis. This is going to be my y-axis. And again, this is going to go up to right here. That was supposed to be a perfectly straight line, so I just wanted to try to do it better. And that looks good. And then this one's going to come down here and go down to 2. So that looks good. And then this one's going to come down here and go to there. I didn't use exactly the same scale. Notice it's a lot wider in the diagram up there, but that really doesn't matter. I'm just using it to get an idea of what we're dealing with. So when I go to integrate this one, I have the same deal. I need to, and actually let me erase this XCM. I'm just going to replace it with the integral that I'm actually doing. So the first integral I'm doing is going to be y dm. So I need that dm to not vary much in y. So that forces me to consider a rectangle like so. Oops. A rectangle like so. And of course, the height of this rectangle is dy, but the width of it is actually, since this quantity over here is supposed to be w, and this quantity over here is supposed to be h, and this quantity over here is supposed to be negative d, we can see that this width is basically w minus the y function, which is going to be x as a function of y. This guy, which was y2 equals h over wx, is now going to be x is equal to w over h times y. So I'm just going to go from w over h times y to w. But as you notice, once I get down to once I integrate from 0 up to h, I can't use the same function to integrate from 0 down to negative d. So I've got to draw another rectangle here. And that rectangle, again, needs to be very narrow in y. So I'm drawing it this way. So again, I get dy, and this function, which was y1, is equal to negative d over w. X is going to become x is equal to negative w over d times y. And I couldn't have made that any smaller. So let me make that fixed, or let me fix that a little bit. Okay. So what I said was this was y is equal to negative d over w x, and that was supposed to be what I call y1. So now what I'm going to say is x is equal to negative w over d times y. Okay. Now that I've worked out those details, which are admittedly kind of messy there, everybody sees that they're messy. So we're going to have to work this out like this. I'm going to say integral of y times sigma, because the dm is again going to be sigma dA. The dA, of course, is going to have that dy in it, but it's also going to be w minus x. And this is time, that w minus x is the width of that triangle times dy. And I'm going to integrate that from y equals 0 to h. But that's just going to get me the top half. The other half is going to be y sigma times, now it's going to be w minus, w minus y. And this one, maybe we call that y2 just to be careful, or call this x1 to be careful, and call this one x2 to be careful. So this is x1 and this is x2 times dy. Again, in this case, we're going to integrate from x equals 0 or y equals 0 to y equals negative d. Any questions on that? All right, so let's see what happens. I can check this work too, because I can break it up into two right triangles and use the 2/3 rule and double check. If this went from h to negative h, it would be symmetric about the x-axis, and you'd expect the y component to be right on the x-axis at x equals, or excuse me, at y equals 0. But that's not what this is. So I'm going to continue on and say equals, and I'm going to pull out my sigma right there, and I'm going to integrate. In this case, I'm going to say y times w, so this is wy minus, now x1 was what we wrote at the top, so that's w over hy, so this is going to be w over h y squared, because the y was there, but I had to multiply by the other y. So that's what w minus x1 times y is, and then that's times dy, and this is going to go from 0 to h, and this is the integral from 0 to negative d. And again, I didn't get rid of my sigma yet, so let's put the plus a little closer over here, and I'll put the sigma right there. Okay, so I now have the sigma. I'm again going to distribute that y through there, so I'm going to get wy minus, now x2 is negative w over d times y squared dy. Okay, does everybody follow that? Anybody have any questions? All right, so things getting real now. I'm going to have my sigma still out here. The integral of wy is w over 2y squared, so that's w over 2h squared. So I'm going to say w h squared over 2 minus, now this one's going to integrate to w over 3h times h cubed. Notice that basically we have something with units of meters cubed in the first term, and then w times h cubed would be meters to the fourth, but it is divided by h, so that's meters cubed as well. So these do actually allow us to add them to each other unit-wise. That's a necessity, and it would be a nice little check to prevent you from making a careless integration mistake. So now I've done the first integral, or the first half of the first integral. I've got another sigma over here, And this one's going to be the same thing. It's going to be W, but in this case, it's W over 2. And we're going to get y squared becomes negative d squared, but when you square it, it's just d squared. So that's what that one is. The minus minus is going to become plus, so I'm going to get w over 3d. And then the integral, like I said, is y cubed over 3. We've already got the 3 down there, but this y cubed is going to be negative d. So in this case, it's going to be negative d cubed, and that negative definitely matters here. Okay, so the negative is definitely going to stick. You can see right here that this exponent of 3 is going to cancel out with that h there, so I get wh squared. And of course, this is 1/2 minus 1/3. So this is 3/6 minus 2/6. So I get basically 1/6 wh squared. Sort of the same thing seems to happen here. I get 1/2, and the other side I'm going to get minus, and it's going to be 1/3. So I'm going to get 3/6 minus 2/6 again, and this time it'll be wd squared, because as I can see here, this 3 is going to cancel out, leaving a 2, and that d is going to disappear, and now they match. So ultimately, I am going to say that my answer is sigma times wh squared over 6. That's for the first term. And of course, I got a sigma in the second one too, but that's also going to be 1/6. And it's going to be plus, so that's 1/6, and that'd be wd squared. So that's that whole integral, which we could, in principle, write as sigma w over 6 times h squared plus d squared. That's probably the simplest way we can write it. Any questions on that one? Pretty nasty, huh? All right, that's the top integral. We also got to do the bottom integral, which is the integral of dm. The integral of dm is slightly different in this one compared to the top one, because we're integrating the other way. So this is going to be the integral of dm, and that's going to be, in fact, the integral of sigma. Now we're going to have everything but the y in there, so I don't have that y anymore. I'm going to integrate from 0 to h, and now I've got wy, or excuse me, I got w minus w over h y dy plus integral from 0 to negative d of sigma again. And this time I'm going to have w plus w over dy. And all that times dy. Now, clearly the sigma is going to be there, so I can deal with that. And what I have is the integral of w with respect to y, which is just going to become wy. And then when I evaluate that at h and 0, I'm just going to get wh. So this will be wh. W over h times the integral of y becomes negative w over 2h y squared, but that's going to become h squared. So this will be negative w over 2h h squared. That handles that first integral. And then plus sigma again. Now I'm going to get this same thing. This will be w, negative w over d. Actually, negative wd. Sorry about that. So negative wd, because the integral of w is just y, and then I evaluated at negative d, and then again minus 0. So that's negative wd. Now when I integrate w over dy, that's going to give me positive w over 2d y squared, which would be just plain d squared, because the negative cancels out when we actually square it. Okay. So we can now see that this d squared is going to cancel out and leave just an exponent of 1 up there. And this h squared is going to cancel out and leave just an exponent of 1 there. So I get wh minus 1/2 wh. So this guy right here is going to be wh times 1 minus 1/2, which is just 1/2. And this one's going to be w over, or wd. So I'll write wd times, now in this case, I've got 1/2 minus 1. So this would be a negative 1/2, like that. Okay. So my ultimate result in this particular case, I'm going to come back here and write it. Let's say we'll write it right there. So I've got a common sigma and w. That's in both terms. In this case, I get a 1/2 h. And in this one, I get a negative 1/2 h. Oops, negative 1/2 d. Sorry about that. So this is going to become, and I don't know why I'm writing in purple, but anyways, here we are. This would be sigma w over 2 times parentheses h minus d. And this is just god awful, way worse than I thought. All right, so let's start putting this together. I've got to have this part of the formula. So what I'm going to do is lasso all this stuff. Copy. And now I'm going to paste over here. Now that got everything plus what I didn't need, but the main thing is I got everything, so we're golden on that. Now I just need to move it where I can make use of it. I'm going to put it right there. Now I'm going to jump up here and erase some extra extraneous stuff. For instance, all this. That looks good. So the y center of mass is supposed to be sigma w over 6 h squared plus d squared. And then that's going to be sigma w over 2 times h minus d. Whoa. Now, I did all this with symbols, but we can put the numbers in, and this will make it a little bit more straightforward. The main thing we're looking at here is the sigma w's canceling out with the sigma w, and we're going to get 2 over 6, which would be 1 over 3, times h squared plus d squared over h minus d. So that's just a nightmare, but let's plug it in. We got 1/3 h squared plus d squared. The h was 3 and the d was -2. So I'm going to say 3.00 meters squared plus -2.00 meters squared divided by 3.00 meters minus 2.00, oh, minus -2.00 meters. Okay, so that in turn turns out to be 1/3 of 9 minus 4. So that would be 5.00 meters squared, because when I square it, it becomes meters squared. So that'd be 9 meters squared minus, or excuse me, plus 4 meters squared. So actually, I just subtracted that by mistake. So let me fix that. No. So 9 meters squared plus 4 meters squared gives me 13 meters squared. Whoa, Nelly. So I'll say 13.0 meters squared. And then 3 minus -2 is the same thing as 3 plus 2. So that's going to be divided by 5.00 meters. We can clearly cancel out one of these meters with that guy down there. And we're going to get 13/15. Oops. Looks like the result will be 13/15 meters. And that says YCM is equal to 13/15. Let's go ahead and write that out. 13 divided by 15 gives me 0.866. So I'm going to say this is 0.8667 meters. Now we're hoping that's right, and if I didn't make any careless mistakes, it should be right. And we can test that, because what we had, of course, was a block that went up 3 and over 5. And 5.00 meters here. And then we had a block that went down 2 and over 5 as well. So we also had that the whole thing had a mass of 30.0 kilograms. So if I calculate the area of the top, that's going to be 1/2 the base, which would be 3.00 meters, times the height, which is 5.00 meters. So that's 7.50 square meters is the area of the top. The area of the bottom is going to be 1/2 2.00 meters times 5.00 meters. 2 times 5 is 10, so this is going to be 5.00 meters squared. So the reason why I'm doing this is I know that the area over the top divided by area total should be equal to the mass of the top divided by the mass total. And area of the bottom divided by the total area should equal the mass of the bottom over the mass total. Oops. Dang it. So using that, I can determine what the mass is. So I can now say that the mass of the top is equal to area of the top, which is 7.50 square meters. And then I divide it by the total area, which is 7.5 plus 5, 3 of those would go to making it 10, so this would be 12.50 times 30.0 kilograms. Now that gives me the mass of the top. So 7.5 divided by 12.5 times 30, that gives me 0.6, by the way, times 30 gives me 18. So this one's going to have a mass of 18.0 kilograms. And the mass of the bottom is going to be 5.00 square meters divided by 12.50 square meters times 30.0 kilograms. So 5 divided by 12.5 gives me 0.4 times 30 gives me 12. So this one should have a mass of 12.0 kilograms. Now I can say the y center of mass is the one that I'm curious about. So the y center of mass, I'll start calculating by saying that the first mass is 18.0 kilograms. That's for the top. Now its y center of mass should be basically 2/3 of the way down. Well, if I start at the top and go down, that's 3 meters to the bottom. So 2/3 of that would just be 2 meters down, which is 1 meter up. So I'm going to call that 1.00 meters. And then the other one is 12.0 kilograms times, now this guy, I need to go 2/3 of the way from the bottom up. That's also 1/3 of the way down. So 1/3 of 2 would be 0.666. So I'm going to say 0.6667, and I got to put a negative in there because it's actually below the x-axis, and all that should be divided by 30 kilograms. So if I do 18 times 1, which obviously you don't have to multiply, plus 12 times negative 0.6667, that gives me 9.996, 9996 actually, kilogram meters in the numerator, divided by 30.0 kilograms. That gives me 0.333. I was worried about my signs integrating from 0 to negative d and stuff like that. That was what was really worrying me. So that's why I wanted to confirm. And this looks like I did, in fact, have some fatal error in it. So we've got that one. What do we get for the other one? We got 2/3 of W, and of course W was 5, so that'd be 10 over 3. That'd be 3 would give us 9, so that'd be 3 1/3, so that's 3.333 was supposed to be the x center of mass. We can check that one too. Let's see, the x center of mass is equal to, again, we have an 18 kilogram. Now the y center of mass for that guy, which was the top, by the way, the x center of mass for that one would be 2/3 of the 5. And 2/3 of the 5, like I said, is 10/3, which is 3.333. So this is going to be 3.333 meters plus 12.0 kilograms times, in this case, it's going to be the same thing, 3.333, which I think we both can now figure out it's going to be 3.333, or all of us can. All that divided by 30 kilograms. So if I do this just to double check, it's going to be 18 times 3.333 plus 12 times 3.333. That gives me 99.99 divided by 30 gives me 3.333. Okay, so that does seem to be what we got for our, well, 2/3 of W. Yeah, that's 3.333. Darn it. 2/3 of 5.00 meters is equal to 10.0 meters over 3, which is 3.333 meters. Okay, so we got that part right. I'm thinking the negative problem. Yeah, I'm not really sure what happened with the YCM. So everything I told you about how to do it should be right. I might have made a careless arithmetic mistake, but the XCM is definitely right. So I'll write that here. Okay. Any questions on that? All right, so that turned out to be what was going to be two separate problems by dividing it up and showing the areas, how I use the areas to figure out what the mass of each one was. That kind of handled the other problem that I was going to do. So I'm pretty good with this in general. We've now calculated a center of mass of a discrete collection, and we've calculated the center of mass of a really nasty continuous matter. I don't know what went wrong. I'm looking at that second integral in the integral of ydm, and I said that was w minus x2. And that seems right because when I get up to y equals negative d, then I would get basically a positive w because the y would be negative d times negative w over d. So that'd be a positive w. And that actually gives me the height at the, or excuse me, the width of the rectangle at the very bottom point is 0, which I expect. If I try the value at, let's say at y equals 0, then I just get W, which should be right as well. So that all looks right in using W minus X2. I don't know what happened. So it could be in the first integral, it could be in the second integral. I could have made a small mistake in both of them, all sorts of good stuff. But be advised, the main thing is I did handle the X center of mass properly, and I showed you how to do it discretely. If anybody wants to attempt to find out what I did wrong on this, I will definitely give you significant extra credit. So I'm going to write this black line here and say, but anyways, you guys can do that if you want. Now we've only got 4 minutes left. And what I really wanted to do next, now that I've done all the chapter 9 stuff, is I'd like to introduce you to the chapter 10 stuff so we can get started on that. So I'm going to do just really quickly, like 2 minutes. Uh, what I want to remind you is we can have, for instance, a circle. And when you have a circle, you have a very specific radius, which is, let's say, r, you can allow that radius, oops, you can allow that radius to sweep out an angle theta. And this is sort of the definition of radians. So what we found in trigonometry is S is equal to R times theta, assuming theta is in radians. Okay. And remember, basically the rule is that 180 degrees is equal to pi radians. And radian, as you can tell by solving for theta there, a radian is actually a S divided by R. So that's like meters divided by meters or centimeters divided by centimeters, which means it has no units. So no unit really, but it is a pure number and it's very important. So this is our conversion factor that comes in handy. You might need that on occasion. This is the fundamental equation for the arc length. And if you think about it this way, you could say ds over dt, again, keeping r constant, is equal to d theta over dt. And what we find out is that v, or excuse me, that ds over dt is in fact v, and then the r, but that d theta over dt is the angular speed, our angular velocity. Now, if you use radians, it will always, always, always work. But there are sometimes some of these equations don't work unless you do use radians. So it'll take a little experience for you to figure out really what's going on there. But now if I take v is equal to r times omega, and I take the derivative of both sides, I get dv over dt is equal to r times d omega over dt. Well, this is essentially the acceleration. I'd call this one the tangential acceleration. So if you're driving in a circle, it's how much you're speeding up or slowing down is what the tangential acceleration is. And that's equal to, of course, r times the angular acceleration, alpha. But we also have, so I'll box this off, but we also have our old friend centripetal acceleration, which is just v squared over r. So what you now see is really your acceleration can have a sub c, and it can have a tangential acceleration a, and then they're perpendicular to each other. So the total acceleration would be this guy. That's a lot of the main stuff you're getting used to. When we had x is equal to 1/2 at squared plus v0t plus x0, it turns out there's an equation just like that. That is theta is equal to 1/2 alpha t squared plus omega 0t plus theta 0. And when we had v squared is equal to v0 squared plus 2ax minus x0, it turns out there's an equivalent equation. Omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. That's enough to get you guys started. In other words, all those equations that you used before, the wording of them can be identical. And the only difference would be you'd have, instead of meters per second, you'd have radians per second for omega. Instead of meters per second, you'd have radians per second, or degrees per second, or revolutions per second for alpha. All right. So that should be enough to get you started on chapter 10. So you guys are free to go. Thank you very much for coming. I will be posting a practice test today or tomorrow. So just keep an eye on that. I'll send you an email when it happens. Your exam, actually, you meet on Tuesday. So your exam's next week, and that's going to be helping you for your face-to-face exam. So anyways, it'll be posted today or tonight. And I think you guys said y'all meet on Thursday, so you still have plenty of time. But have a good one. I'll wait for the last person to leave in case anybody has any questions.
Thank
I'm
you.
sorry,
Good evening.
can you clarify that one more time? We have an in-person exam next lab period?
Yes, based on the schedule, let me pull it up real quick, and I'll stop sharing the screen so I can talk to you about this. Let's see. So what I'm looking at is the face-to-face exam for people that have labs on Tuesday, Wednesday, Thursday, or Friday. Then their exam is going to occur between April 2nd and April 8th. If I look at the calendar, April 2nd is Tuesday of next week, and April 8th is Monday of the following week. So you guys that have lab on Thursday should have your next face-to-face test a week from tomorrow.
What about this probably only applies to me, the Monday lab, because we just had a lab, not last week, or not this week, but last week.
Right. Yeah. The Monday lab, you're a whole week back. So you'll be taking that on the 8th. Yeah. So
Okay, perfect. Thank you.
yeah, anybody that has my lab that meets on Mondays, you guys will have it a week from Monday. But everybody else has it next week. So just be prepared. And this practice test I'm making up for you should help you with that. I'm only going up through chapter 9. I think that should work. That question, Jennifer?
Yeah, it was what chapters was the test on?
I might make it just to 8 because I really would prefer to have a meeting with you in class before then, and we will. So I might not, but I would prefer a little bit more time. But I'm leaning towards right now it definitely covering chapter 9. If I change it, it would only be to pull it back to chapter 8. So right now, just assume it covers up through chapter 9. I'm definitely not going later than that though. So the exam will not cover chapter 10. There's a definite no on that one.
Okay.
Okay. Don't worry, I'll be gentle on you. You guys are awesome. I'll take care of you. Anybody else? Hannah or Kayla or anybody?
No,
Make
you
sure you
answered my question. I was just sticking around to see if anybody else had something similar.
okay. Make sure y'all did. It looks like everybody did already. Tweeted me or chatted me your name. So y'all have a good weekend and just keep an eye out for the email for when the practice test comes up. Remember that practice test is one, something that gives you extra credit, but two, it's the best way to prepare for any upcoming tests. We have a face-to-face test, like I said, next week for most of you, but the online test will probably occur shortly thereafter. But that'll cover largely the same stuff you did in the face-to-face, so you'll be in a good spot for it.
Thank you. Have a good weekend.
You're welcome. See you, Kayla. Thank you.